Hey everyone, how goes it? And welcome back to Computer Science 146. Today, we're going to discuss binary search trees. Trees are fairly popular data structures used in computing, and a tree is a data structure that can be defined recursively as a collection of nodes, that seems familiar, where each node is a data structure consisting of a value together with a list of references. That also seems familiar. With the only constraint being that no reference is duplicated and none of them point to the root. Now, an easier way to consider this is a tree has a collection of nodes and edges. Whenever we refer to the references, think of those as the edges. Another way that we can view a tree is it cannot have self-referencing edges, have cycles, and also, for argument's sake, be disjointed. Now, this would be an example of a self-referencing edge, which creates a cycle. This is easily a cycle between these two nodes, and thus this cannot be a tree. And this indicates an undirected edge, sometimes just shown with a straight line, but once again, that's the same thing as this. The thing that we have to remember is a tree cannot have cycles. Now, there are a lot of common terms associated with trees, and I'm only going to go over a few of those. First, the root is the topmost node in the tree. Think of that as the same thing as the head reference in stacks, queues, and also generic linked lists. A child is a node's reference which is at a lower level, and the parent is the converse of that notion. So the way that you can think about this would be the parent node of this node, and this would be the child node of this node. Parent and child, much like a family tree. Siblings are nodes that have the same parent. Now, leaves are a node with no children, and we're going to further define that a little later. And there's some other terms that we will discuss a little bit later on. Now, there is a very specific type of tree that's used a lot in computing, and that is called the binary search tree. Now, first of all, the binary search tree is a tree structure, so you don't have cycles. Now we start adding additional rules that make this into a specific kind of tree called the binary search tree. The first one, all the nodes' data has to be comparable in some way. Next, in a binary search tree, nodes have at most two children, a left child and a right child. Now, the relationship between the left child and the parent is the left child's value must be less than the parent's value. Similarly, the right child's value has to be greater than the parent's value. And in this case, we're also going to establish that we cannot have duplicate values in a binary search tree. And furthermore, with our definition, we're just going to assume that the leaves are the null references. So to the side here, you see an example of a binary search tree. Here's the root value, and notice all the values to the left of the root are less than the root. And all the nodes to the right of the root are greater than the root. All of these are leaves as they are the null references. And the left and right property applies for any of the subtrees. Like for instance, if we started right here, the values to the left are less than this value, and the values to the right are greater than that value. So for a binary search tree, nodes' data has to be comparable. The left children are always less than the parent's value. The right children are always greater than the parent's value, and there are no duplicates. With that being said, let's go ahead and start setting up the structure for a binary search tree. As you can see, we've already set up our project and we've created our class, the linked binary search tree. Now we want to make this binary search tree a generic type, so it can be a binary search tree of anything. So we define this as a linked BST of type T. However, we understand that type T is basically a variable for object types. Everything in Java is assumed to inherit from the base class object. Any class that you make inherits from the class object. However, the class object is not comparable. So if we want to adhere to one of the first rules, that all of the data in a binary search tree must be comparable, then we need to redefine this type T here. In order to guarantee that this type T is comparable, we're going to say this type T extends comparable of type T. Now what this does is it takes this interface and now extends it to the type comparable. Now any type of object that we're going to use inside this binary search tree must implement this comparable interface. Inside of this comparable interface, as we know, there is a method definition, and we'll get to that a little bit later on. For right now, let's continue to define this linked binary search tree. As we're starting with the linked implementation first, one of the fundamental ideas was establishing each one of the nodes. So just like a generic linked list or a linked stack or a linked queue, we're going to first start out with a private class, but this time just simply call it node. Now in the definition, each one of the nodes contain the data and the references. So first, we're going to go ahead and create the type T data. And that's going to be the data contained in the node, which once again is comparable. Next, we know that a binary search tree, every one of the nodes has at most 2 children, a left child and a right child. So we need to define those references here as well. Node left child, and also node right child. Now I'm going to create a simple constructor that's going to only set the data. Public node TAdata, and we're simply going to assign data to point to A data, and also left child points to right child, which also points to nothing. Now that we have this class node, what we can do is use this class in order to create the nodes. The first one, and arguably the most important one, is private node root. Think of this as the same thing as the head inside of the linked lists. Now we're just going to create a constructor, public linked BST, and we're just going to establish that the root is nothing. Now let's see what we can do with this type so far. I'm going to go ahead and create a new class, and I'll just call it the BST tester. So from right here, we can create a linked BST. However, we need to think about a type that is comparable. Let's keep this simple and just create an integer, and call it the iBST, and construct it. New linked BST of type integer. And now we've constructed it. Now once again, remember, this linked binary search tree, the generic type extends comparable. This worked because we know we can compare integer values. But watch what happens if I do this. Linked BST of type object. OBST is equal to new linked BST of type object. This gives me a syntax error because the type object does not implement comparable. We can only use this binary search tree if the data is comparable in some way. Now that we have the tree, well, we need to be able to add data to it. So let's take a look at how we add information to a binary search tree. So the way that we add an element to a binary search tree is first we construct a new node. This is very similar to how we added information to the generic linked list, the linked queue, and the linked stack. Once you've constructed the new node, then you start from the root node. Then you go recursively left and right until a leaf, in other words, a null element is found. We then replace the leaf's reference with the newly created node's reference. Looking at an example, let's say that we're going to add the value 7 to this binary search tree. The first thing that we do is we construct that new node with the data. So there's our new node, and there's the data. Now we start from the root node. We have to use the properties that we know about a binary search tree in order to place this in the correct location. We understand that the left child is always less than the parent, and the right child is always greater than the parent. So starting from right here, this is not a leaf element because it is not null. Also, 7 is less than 8, so we have to go left. So now we're here. This is not a leaf. Also, 7 is greater than 2, so we must go right. This is not a leaf. 7 is greater than 4, so we have to go right. And now we finally reached a leaf, this null element down here. What we then do is replace the reference in this node's its right child with this new node's reference. And so this places that node to there. And we're done. Let's see how this looks in code. So we're first going to start out. Public void add TA data. Now we're going to start off with the first check. If we don't have a tree, in other words, if the root is nothing, then all we need to do is point the root to this new node, passing in a data. So now we've taken care of the case if the root was null. But if we did have a tree, so the root was not null, what we need to do now is recursively add the element. Now to make this simple, what I'm going to do is separate out the recursive call into a different method. Now we're going to make this private and node. This method is going to return the reference to a node. We're simply going to call it add, and then we're going to overload it by passing in first node a node and also TA data. Now from here, we're simply going to call this version of add, starting from the root with a data. It's important to note that recursion is loop-like. And just like with loops, we need a stopping condition, a halting condition. In this case, the halting condition is when we reach a leaf. So in other words, if we pass in a node, so if a node is equal to null, then we have reached a leaf. What we're going to do is assign a node to the construction of a new node and a data. When we call this constructor, it constructs an instance of this node, assigns the data, and then this becomes the reference to this value. This is also the reference that we're going to return, which is then going to be assigned by one of its parent nodes. But before we get to that, let's worry about some of the other conditions. So if we reached a leaf and it was null, we construct a new node, and then we add it here. However, if the node was not null, so it does exist, now we need to compare this data versus the data that's inside the node. So we call else if a data. As we know, this data is type T, and that type T extends comparable. This means that we know that there has to be a method defined in every one of these types that make this comparable with something else. Now, inside the interface definition of comparable, we know that that method is called .compareTo. Now we can compare this data with a node.data. But now we notice that there's a syntax error right here. And that's because everything that's inside of the parenthesis of an if or an else if statement has to yield true or false. When we call compare to, this returns an integer value. Now, this is how we can make this work. What we can do is say if this method compare to returns an integer that is less than 0, this indicates that this data, the data that we're trying to add, was less than the data at the node. Now, if that's true, we go left. Now, this could be the case that when we go left, that this node's left child is a leaf. It is null. So what we want to do is assign a node.leftChild is equal to add a node.leftChild with a data. So let's assume, for instance, that a node's left child was null. By recursively calling add left child, what happens is this is pushed on the call stack, this node is null, which then constructs a new node, which eventually is going to return it. Then when we recursively come back, we assign the memory reference, the node, to the left child. Now we do the same thing, but going in the right direction. Else if a data.compareTo a node.data. Now, if this method returns a value that's greater than 0, this means a data was greater than a node.data. So then, a node.rightChild is equal to add a node.rightChild and a data. Now this once again was go right. The last thing that we do is we return the reference a node. Now when we return a node, if we were at a leaf, as we can see, this is constructed, so this becomes the reference to the node that we're trying to add. As we recursively go backwards, we return that reference back to here to then be assigned. And then we return all the way up to the root of the tree. Let's see now how we can add some elements to our tree. Going back to here, we're going to replicate the example. So we're going to have an I binary search tree, and we're going to add in the following data. Add 8. Add 2. Let's see, add 12. Add 1. Add 4. Add 10. Add 16. And now we should have the binary search tree that we have in our example. However, we really can't see those values or do much with them. In previous data structures, something that we started going over to verify if this was working was printing out the values. However, now printing out values have become a little more complicated than just using a for loop. Let's take a look at how we can do this. So in order to approach this, we have to address traversals. And this is a way that we can traverse, in other words, travel, in other words, walk, through a data structure. Now, as we're using a tree structure, it's not as straightforward as linear structures like an array, or a linked list, or a stack, or a queue. So one of the first things that we have to decide on is, what is our policy? What direction are we going to traverse this first? Are we going to go depth first, so go down each level, or are we going to go breadth first? In other words, address all the elements level by level by level. Now, depth first is assumed to be stack-based, and breadth first is assumed to be queue-based. Looking into this a little further, if we were to choose depth first in order to walk through this tree, well, this also comes with some issues. What do we do first? Do we recursively go left? Do we recursively go right? Or do we process the nodes first? Now, if we're talking about depth first traversals, then we worry about these three specific operators. So whenever you see left, that means recursively go left down the tree until we reach a leaf, and then backtrack. In other words, follow this arrow backwards to a previous state, and then resume going in the other direction. Right simply means recursively going right down the tree, doing the same thing. Now, process, that's more or less an empty verb. Think of it like this. It's a variable for some sort of action. So the version that we're going to show is printing these values. So when you see process, you can substitute that with printing. Now, the combination of left, right, and process actually creates different versions of depth-first search. There's three major types: pre-order traversals, in-order traversals, and post-order traversals. Now, the way that a pre-order traversal works is you process first, recursive left, then recursive right. So in other words, if we start at the root right here, we're going to process this, then we're going to recursive left. Then we're going to process this, then recursive left, then process this, then recursive left. This is a null element, backtrack. Recursive right now. This is a null element, backtrack. We're done processing this, backtrack. Now we have to recursive right, then left, backtrack, right, backtrack, backtrack, backtrack. Now we can finally go recursive right from here. Then we go left, left, backtrack, right, backtrack, backtrack, right, left, backtrack, right, backtrack, backtrack, done. Another way that we can look at a pre-order traversal is if we started from the root and we traced around this graph, node by node, going counterclockwise. Then anytime we pass by a node to the left, then we process it. So the pre-order traversal for this tree following that rule will be 8, 2, 1, 4, 12, 10, 16, and you're done. Let's take a look at the pre-order traversal in code. Starting from right here, we're going to go ahead and create the public void print pre-order. Now, as this depth first traversal is stack based, what we're going to do is implement this recursively. We know that when we create a method that is recursive, it utilizes the call stack in order to process that information. Once again, I'm going to separate out the callable method, like an add, with a recursive method. So once again, this is the callable method print pre-order, and now I'm going to create the recursive method private void print pre-order, where we pass in node a node. Then from this method, we start print pre-order from the root node. Now we know that this is going to be recursive, and we have to worry about our halting condition. And just like add, our halting condition is when we reach a leaf. So if a node is equal to null, we return. However, if that's not true, then what we have to do is process left, then right. In this case, our process is print. So we're going to system.out.println a node.data. Then we recursively go left, which means we call print pre-order with a node's left child. Now once we have recursively gone left, we recursively go right. Print pre-order a node.rightChild. And that's it. That's how we write a print pre-order traversal for this tree. Let's see if it works. Going back to here, we're now going to call ibst.print preorder. And let's see if we get the same result that we had in our example. And sure enough, we do. Now let's take a look at that same example in closer detail. Now this depth-first traversal is based on the stack data structure. What we have to the side here is the call stack. So let's just assume that the main method had already been pushed on top of our call stack. From there, what we're going to do is call that print pre-order starting from our root, so it looks like this. For argument's sake, we're just going to compartmentalize this into this right here, which is still the print pre-order method that was called, which starts from the root. Now this called the recursive version of print pre-order, which pushes this code on top of our call stack. Now we know that print pre-order passed in the reference to the root. So starting from right here, we can then visualize that we're starting from this root node. Now we can see that the root is not null. So then we process that data, in other words, we print it out. Then we recursively go left, which now travels down to the left child. And as we have called this recursive method, this has now been pushed on top of the call stack, and it starts it over again. Notice that this is still sitting in memory, and it's waiting for this to complete before it can resume and go right. Now we're running the top thing on our call stack. So, as we can see, this node is also not null. So once again, we process it by printing it out, and then we push another call going to the left child here. Now this starts out, this node is also not null, so we process it, and then push the left child on top of there. Now, we are at a leaf. In other words, a node is equal to null. This means we return, and when we return, this automatically pops this off of the call stack, and we resume where we came from. So when this gets popped off, we go back. We backtrack to this previous node, which left off calling print preorder on its left child. Now that that has completed, we then move to the right child, which then pushes this method on top of here. It is null, it returns, and we're done. Now that node has completed. Now once this method completes, it is also popped off of the call stack, which now this backtracks to the node value 2. It was waiting on everything to process from its left child before it can move on to the right child. This then pushes this on top, which traverses right, which then traverses right, which then it's going to go left, then right, and then it's going to keep going through this exact same process until every one of the nodes that are reachable from the root are printed out. So a few traversals later, we end up with the same result. Now let's take a look at some of the other traversals that work in a very similar way. The next type of traversal that we're going to do is called in order. In order shuffles around process left and right. In order goes to the left child first. It recursively goes left, then it processes, then it recursively goes right. Let's see what this looks like. Public void print in order. And once again, we're going to create the recursive version, private void print in order with node a node. Now from the callable method, we call print in order starting from the root. Then, if a node is equal to null, return, because it's a leaf. Now the difference starts here. First, we recursively go left. Print in order a node.left child. Then we process the node. System.out.println a node.data. And finally, we recursively go right. Print in order a node.right child. Right. Let's see what happens when we call the in order traversal on the same binary search tree. ibst.print in order. Now running this, we start from right here, and look what all the values are. They are in ascending order. The in order traversal shows that as we are adding data to this data structure, it always remains sorted. Binary search trees are based on the algorithm binary search, where everything to the left of a value has to be less than that value, and everything to the right of that value has to be greater than that value. Taking a look at this concept once again, as we just explored, the in-order traversal goes left, process, and right. And by doing that, it can print out or process all the nodes in order. Taking a look at this example, we can see that all the nodes to the left of this value is less than this value. Everything to the right of this value is greater. By simply having this property, all of the values are sorted automatically as they are added to this data structure. Now finally, the last type of traversal in the depth-first version is called post-order, that goes left, right, and then process. Now this is very similar to pre-order, except instead of passing by the left, it's whenever you pass by the right of a node. So watch this. If we're doing post-order traversals, then it's going to be 1, 4, 2, 10, 16, 12, 8. Now the last type of traversal we will address right now, but we're not going to go into a lot of detail about it. If we were to take the other strategy, instead of depth first, we do breadth first. This is queue-based. And the way that this works is you start by enqueuing the root node. Then you start the process where you dequeue a node, enqueue its children, and you keep doing this until the queue is empty. And in this way, Instead of going via the depth, you go via the breadth. In the next lectures, we're going to start exploring more details about binary search trees, which include the method search and also how do we remove elements from a binary search tree. With all that being said, I'll see you next time.